In this lecture, I want to talk about habitability and the possibility of life around other stars from the context of different types of stars and what we might expect in terms of what sorts of stars we might expect to be the most likely centers of habitable planetary systems. We've looked many times at this classification scheme on the HR diagram, from hot stars to cool stars, from dim stars to bright stars. The brightest stars in the main sequence are the O and B type stars. They're the hottest and the brightest, down to sun-like stars, G-type stars like the sun, all the way down to the dim, cool K and M type stars. One of the things that we maybe don't stress often enough is the luminosity, the brightness scale on the HR diagram is exponential. So O and B type stars are many, many times brighter than the sun. Not just twice as bright, but hundreds or thousands of times brighter. And K and M type stars are way, way dimmer than the sun. Not just half as bright, but as little as 1% as bright. So if we use the sun as our meter stick for stellar properties, we call the brightness of the sun one brightness unit and the mass of the sun one mass. K and M type stars can be between 0.2 and 0.7 solar masses. So around half the mass of the sun, maybe a little more, maybe a little less. But the brightness can be from 30% all the way down to less than 1% the brightness of the sun. A and F stars, which are brighter than the sun, are not that much more massive. Bright F star might be twice as massive as the sun, but 20 times more luminous. So it's not a one-to-one correspondence, not a one-to-one ratio. If you double the mass of a star, that increased pressure on the star makes that 20 times brighter. As for the O and B stars, B-type star might be 6 times more massive than the sun. An O-type star might be 60 or even 100 times more massive than the sun. A B-type star is thousands of times more luminous than the sun, however, and a bright O-type star can be 1,000,000 times brighter than the sun. So there's a huge range from less than 1% as bright to 1,000,000 times as bright when you look at the different main sequence stars on the HR diagram. And there are examples of all of these stars in our galaxy. When we did the HR diagram lab, we saw that O and B stars are comparatively rare compared to G, K, and M stars. When we say the sun is an average star, which we say all the time, astronomers say all the time, the sun is an average star. What do they mean? Well, they mean there are stars that are a tenth as massive and 10 times as massive. There are stars that are a tenth as bright and 10 times as bright, or is a hundredth as bright and hundreds of times brighter. That does not mean the sun is a particularly common type of star. In fact, if you look at the ratios, the abundances of these different types of stars, and you saw some of this in the HR diagram lab when you just plotted the nearest and brightest 100 stars to our sun on an HR diagram. The vast majority of those were M-type stars. In fact, M-type red dwarf stars make up almost 3/4 of the stars in our galaxy, together with K-type stars, which make up 15%. 75 plus 15 is almost 90% of the stars in our galaxy are dimmer than the G-type stars that our sun is. So while our sun is average in the sense of being in the middle, there are way more stars dimmer than the sun and lighter than the sun than there are stars that are bigger and brighter and hotter than the sun. So that's something to keep in mind. G-type stars make up about 7%. A and F together only make up about 3% of the stars in the galaxy, and O and B-type stars only make up about 1% of the main sequence stars in the Milky Way and in any typical galaxy. So if we're interested in looking for extraterrestrial life, which is what we've been talking about in the past few videos, where should we look? Well, you might be tempted to say, well, look, we know a G-type star like the sun can be the center of a habitable system, so we should look at G-type stars. Well, except that they only make up less than 10% of the stars in the galaxy. So if we constrain ourselves to looking at only sun-like stars, we will miss between 3/4 and 90% of the stars in the galaxy. So it's worth asking ourselves, can we imagine habitable planetary systems around K-type or M-type dwarf stars. Some things to think about with regards to the lifetime of a star system. We've talked about the fact that our sun has been around for about 5 billion years, probably has about 5 billion more before it starts to go haywire and swell into a giant and have its helium flash and make things unpleasant for those of us here on Earth. But 10 billion years is a nice long time. We've had plenty of time for life to form, evolve, diversify, cover the surface of the planet in the first 4 billion years or so. More massive stars, we've talked about this, because they are heavier, because they squeeze their core with a greater pressure, burn their hydrogen fuel faster, and reach that crisis point of having their helium flash and then maybe a carbon flash and blowing up into red giants and maybe even eventually going supernova. They reach that point faster. An A or an F-type star might only live as a main sequence hydrogen-burning star for 1 or 2 billion years. Remember, if you think about life on Earth, and we talked about this very early on in the course, and maybe we talked about it a few times since then, life on Earth didn't do a whole lot for the first 2 billion years. The first 2 billion years of life on the Earth, there was nothing but single-celled organisms living in the ocean. So if we're interested in advanced life that has evolved beyond simple single-celled organisms and bacteria and things like that, 1 or 2 billion years might not be enough. So while an A or an F star might be the center of a habitable planetary system, that planetary system is not going to live for very long. It would have been long gone by now if the Earth was around a or F type star. O and B stars, forget about it. An O-type star might only, a B-type star might only live for 50 million years. That is a blip of time when it comes to the history of Earth or the history of life. An O-type star might only live for 50,000 years before burning up all of its hydrogen, going through all the stages of fusion, and then blowing up as a supernova. So there's no point in thinking about life around a B-type or an O-type star. There's simply not enough time for life to get started. There's not much sense in talking about A or F stars because a billion years or a couple of billion years is barely enough time for life to establish a global foothold and start to become advanced. And by advanced, I don't mean aliens with flying saucers. I just mean multi-celled organisms and things like plants did not exist on Earth until a couple of billion years after life started. Which means if we're interested in life being able to last for a while on a planet, we should be interested in G-type stars like the Sun or K and M stars, which are lighter than the Sun, which squeeze their cores more gently than the Sun, which burn their fuel more slowly. And a K-type star might live for 20 billion, 30 billion, 50 billion, even 100 billion years on the main sequence, meaning that there could be K-type stars in our galaxy that have been habitable not for just 4 or 5 billion years like our Sun, but for 20, 30, 40. Well, no. The universe isn't 20, 30, 40 billion years old. The universe is only 13 billion years old. But we can imagine that into the future that a habitable system around a K or M type star could last for tens of billions of years. And they could be the most common habitable star system in the galaxy because there are the most of them. So let's talk a little bit about what the habitable zones might be like around a K or an M star. Obviously, the stars are dimmer, so they give off less heat and light. They're cooler, so the light they give off is redder and is going to warm the planet less efficiently. So the habitable zone of a K or an M star is going to be closer to its star than the habitable zone of our Sun. Now, let's remind ourselves what astronomers mean when they say habitable zone. They mean something very specific. When we say habitable zone in astronomy and talking about astrobiology, we mean the region around a star where you could have liquid water on the surface of a planet, like the Earth. So It's a really bad name. We'll talk about why it's a bad name again at the end. But when we talk about the habitable zone, we're talking about habitable in the way that the Earth is habitable. Liquid oceans, liquid bodies of water on the surface, not bodies of methane or bodies of ammonia, not liquid under the crust. We're talking about liquid water on the surface, which obviously requires an atmosphere, and that exact temperature at which an atmosphere will boil away, at which the ocean will boil away, depends on how thick the atmosphere of the planet is. But we can calculate a ballpark surface temperature of a planet, which has to be cooler than 100 degrees Celsius and warmer than 0 degrees Celsius. And where around a star will you get that window where if you put a liquid ocean on the surface of the planet and hold it down where an atmosphere, that water will not boil away and it will not freeze into an icy surface. So that's what we mean by habitable zone. Obviously, a K star or an M star will have a habitable zone that's closer to the star. How much closer? The temperature of a star is not linearly dependent on its luminosity. It's actually roughly dependent on the square root. So if the brightness of a star is 100 times more, the temperature is not 10 times more. It's only 100. Sorry, it's not 100 times more. It's only 10 times more. From this relationship, we can calculate, if you take a rock and put it at a certain distance from that star, what will its surface temperature be? And again, it depends whether it's a light-colored or dark-colored rock, how much sunlight it absorbs. It depends on the greenhouse effect and how much of an atmosphere it has. But ballpark, we can make a guess as to the range of distances around any star where you could have liquid water on the surface. What does that look like? Here's the approximate habitable zone for a G-class star like our Sun, with the orbits of the planets in our solar system and the inner solar system shown: Mercury, Venus, Earth, and Mars. We know that we're in the habitable zone because we know we have liquid water on the surface. We know that Venus is well inside the habitable zone. And Venus probably never had liquid water on its surface, at least not for very long, before it all evaporated away and the greenhouse effect went haywire and raised the temperature to 850 degrees. We know that the habitable zone goes almost out to Mars and maybe all the way out to Mars. In other words, Mars used to have liquid water on the surface but doesn't anymore. So somewhere in between here is the long-term edge of the habitable zone. Mars seems to have almost made it in, but couldn't sustain that global comfortable temperature for a time period of billions of years for whatever reasons. And we talked about those when we talked about Mars. So we just say, ballpark, the habitable zone of the Sun extends from just inside the Earth's orbit to about halfway to Mars's orbit. What would happen if we replaced the Sun with a K-type star? Dimmer, redder, cooler. The habitable zone would move inward. Okay? It would be closer. You would have to get closer to the Sun to be warm enough to have liquid water. Notice that if we replaced the Sun with a K-type star, Venus might have been firmly inside the habitable zone of that planetary system. If we replaced that with a M-type star, maybe 10% as bright as the Sun, the entire habitable zone of that star would be inside of the orbit of Mercury. You would have to be closer to that star than Mercury is to our Sun to have liquid water on the surface. And this raises some interesting issues about the viability of a planet that orbits that close to its star. We're interested in whether M-type stars could be the centers of habitable system because there are so many M-type stars, right? 75% of the main sequence stars in the galaxy are M-class stars. But if a planet has to be that close to its star, is that a problem? We'll talk about that in a second. The other thing I want you to notice that happened as we did this, as we went from G to K to M stars, is that the habitable zones didn't just get closer to the star, they also got skinnier, they also got thinner. The range of distances at which you can have a habitable planet gets smaller. Here's a diagram that shows that. If we look at a sun-like star, a star half as bright as the sun, and a star a third as bright as the sun. What happens to the habitable zone? For the sun, it's maybe 0.9 AU out to almost 1.5 AU. If you decrease the brightness of the sun by half, it goes from just under the 1 AU, the Earth would be right on the edge of this half a sun habitable zone, down to a little less than 2/3, so inside the orbit of Venus. If you go down to 1/3 the brightness of the sun, Venus winds up smack in the middle. You go from 80% the distance to the Earth to about 50%, about half. But if you look at the width of this habitable zone, it's actually getting not just closer and closer and closer to the sun, but it's getting narrower and narrower and narrower. The habitable zone of our solar system is about half an astronomical unit. The habitable zone of this hypothetical solar system, around a star half as bright as the sun, is from 0.64 to 0.99 is only 0.35 AU from the inside edge to the outside edge. The habitable zone of this, from 0.51 to 0.8, that's only 0.29. That's less than 0.3. So the size of the habitable zone has decreased as the star in the center gets dimmer and dimmer and dimmer. What does that mean for the habitable zones of dim stars, K-type stars and M-type stars? Well, it means if they're very narrow, the probability that we wind up with a planet that happens to be there gets lower and lower, right? If the planets just kind of form at random, and one of them's got to be in the habitable zone to be habitable, the narrower the habitable zone is, the smaller the probability that a planet will just wind up there. So, while there are lots and lots of M stars, their habitable zones are very narrow, and it might just wind up that there aren't any planets in them, because the probability of one winding up in such a narrow slice of the solar system's orbits, the possible orbits, gets smaller. You can think of it as throwing darts at a dartboard. The smaller the target is, the less probability that there will wind up being a planet in that narrow strip. There are other issues about orbiting very close to a very dim star. One of those issues has to do with the fact that, I'm missing a slide here. There is some evidence that small stars, because there's less kind of gravitational pull holding them in, are more unstable and more prone to violent outbursts, like super duper solar flares. And if your planet, in order to be habitable, was really, really close to that star, you'd be getting cooked by these solar flares all the time, because the sun is more volatile. Its brightness and its kind of surface stability is less than the sun. So there's some evidence that surface life could be hard to maintain on an M-type star that was prone to violent outbursts if you are right up, 0.2, 0.15 AU away from the sun, very, very close in. You would be getting blasted by these outbursts and solar flares and eruptions all the time, which causes a bunch of radiation and a bunch of stuff that's not good for living organisms. The other problem, which is probably more common and more serious and more definite, has to do with tidal locking and synchronous rotation. Way back when we talked about Mercury, I said file away this tidal locking phenomenon in your brain, because it's going to come up again, and this is where it comes up again. Remember, Mercury has got a weird rotation to orbit ratio where it spins on its axis 3 times for every 2 times it goes around the sun, and that synchronization is due to the tidal forces between the sun and Mercury has this property and Venus and Earth and Mars don't, because it is so close to the sun and experiences greater tidal forces than the other terrestrial planets. What is a tidal force? Remember, it's due to the fact that gravitation pulls stronger on the close side than the far side, so it tends to stretch the object out, and as it rotates, that causes the object to be slightly angled off center, so the gravitational pull between the objects is slightly off center, and that tends to slow the object's rotation down. This is why one side of the moon always faces the Earth. The tidal force between the Earth and the moon has slowed down the moon's rotation until it's synchronized with its orbit. The moon is actually slowing down the Earth's rotation. A day now is 24 hours. A day 3 billion years ago would have been more like 19 or 20 hours, because the tidal interaction between the Earth and the moon is slowing down both of their rotations. The Earth is bigger and heavier and the moon is smaller, so we're having a bigger effect on the moon than the moon is having on us, but both objects are being slowed by this tidal interaction. Now, Mercury is not doing much to the sun. The sun is billions, trillions of times more massive than Mercury. But the sun's tidal interaction with Mercury has slowed down its rotation until it has this weird 3-to-2 resonance of 3 spins for every 2 orbits. I think that's it. 3 spins for every 2 orbits? Yeah. 3 days every 2 years. For a planet, imagine a planet that was half as far, a third as far from its star as Mercury. It is going to be subject to tidal slowing, to the point where it may become tidally locked to its star the way the moon is tidally locked to the Earth. In other words, one side of the planet would always face the sun, and the other side of the planet would always face away from the sun. Obviously, these sizes are exaggerated. The planet's not as big as the sun. Which means one side of the planet would always get sunlight and be warmed, and the other side of the planet would always be in darkness and be cold. Can we imagine a habitable planet with only one daytime side and one nighttime side? Liquid water only on one side of the planet? What would the weather be like on a planet with an atmosphere that only one side got sunlight and the other side never got sunlight? It would be a very strange planet. What would probably happen is that one side would get way too hot all the time and the other side would get way too cold all the time, and only this region, this kind of stripe in between the hot side and the cold side, would remain relatively temperate all the time. So it's difficult to imagine a planet having long-term habitability that had this completely synchronized rotation to its star. At least it would be very different. It couldn't be like the Earth. It would be very different from the Earth. In a very science fiction-y kind of environment to think about a planet that's always day on one side and keeps getting hotter and hotter and hotter, and always night on one side and keeps getting colder and colder and colder. So we might want to rule out tidally locked planets entirely from our discussion of habitability. Let's just say if you're so close to the star that you're going to be tidally locked, you're off the list. We're not going to talk about you anymore. Maybe we're wrong, but we're not going to talk about planets that are tidally locked. And we can start cutting down the search space of what types of stars and what types of planetary systems we think might be habitable by applying these various criteria. So let's look at a graph. So on the horizontal axis, we've got how far the planet is from its star. 1 AU is the distance to the Earth. 10 is about the distance of Jupiter. 0.1 is inside the orbit of Mercury. And on the vertical axis is the luminosity of the star in terms of the sun. So 1 star brightness is the sun, would be here. A KRM star would be here. F star would be up here at about 10. Our solar system has a habitable zone that stretches from about half to 1.4 AU. These are the planets in our solar system: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and Neptune. Only Earth is in the habitable zone, so the green strip is the habitable zone for different brightnesses. From just outside Venus to just inside Mars, and Earth is right in the middle. What can we rule out right away? We can rule out anything above here, as those stars don't live long enough. We don't have to worry about them. Those stars are so bright that they burn themselves out in a few billion years or less. We can rule out any star or any region of a planetary system where the planet would have to be so close to the star that it gets tidally locked. that cuts out this whole region of the space right here. We can rule out anything more than about 2.5 times as bright as the sun, because it won't live long enough for its habitable zone to be livable for more than a few million years. We can rule out anything down here, anything with a brightness less than about half of the sun. You would have to be so close to it to be in the habitable zone that you would be tidally locked, and we don't want to think about those kind of weird planets. Again, we could be wrong, but it seems like a pretty inhospitable planetary environment. So anything with a brightness less than about half the sun, we rule out. If we then look at the different types of stars, G like the sun, K type stars, it looks like the place with the biggest slice here, the biggest section of habitable zone that could be occupied, are your G-type stars like the sun and your K-type stars. The M-type stars, even though there's the most of them, you got to be so close to them to be habitable that you cause other problems. So if you had to ask, what's the best place to look for habitable planetary systems? The answer is probably brighter than average K-type stars, stars between a brightness of, say, 60% the brightness of the sun and the brightness of the sun. That's just a guess, but that's a guess based on our best available information about the sun, or about stars. When we talked about the Drake equation, one of the things I mentioned was that, look, all those terms in the Drake equation are guesses, but as we've moved from, when was Drake, 1965, 1968, to 2022, some of those things that were guesses 40, 50 years ago are not guesses anymore. As we have satellites like Kepler and TESS discovering planetary systems around other stars, this question of how many stars are in the, how many planets are in the habitable zone of a typical star in another 15 years might not be a guess anymore. We might have a really good number to help guide us. So we think that G-type stars like the sun, we know are habitable. Brighter K-type stars are probably also quite habitable, and because there's more of them than G-type stars, might be a really good place to look for extraterrestrial life. Now, one thing to keep hammering is that habitable zone refers to something very specific. It refers to Earth-like surface habitability with liquid water. That does not mean that objects outside of the habitable zone could not be habitable. Case in point, something like Europa, well outside the habitable zone, does not get nearly enough sunlight to have liquid water on the surface. In fact, its surface is frozen solid. But we have many reasons to believe that underneath that solid surface is liquid water, and that a heat source from inside of Europa, caused by the tidal interaction with Jupiter, could be enough to fuel life. Same with Ganymede, same with Titan. Titan has liquid on its surface, not liquid water, but liquid methane and ethane. Could we imagine a habitable planet where methane and ethane are the liquid? Maybe, maybe not. But we should caution ourselves against thinking that Earth-like habitability is the only kind of habitability, especially if we're willing to imagine things that live in liquids other than water, things that live with compounds that are other than carbon compounds. We might be able to imagine whole different ways for life forms to exist. This raises a really interesting question, which is, if it's possible for an object like Europa or Ganymede or Enceladus or Triton or Titan to have subsurface water that's heated by some other process, tidal heating or whatever, we can imagine habitable planets around stars that are not even really stars. There's a type of star that we have not talked much about in this course, I don't think, which is a brown dwarf. And the reason I didn't talk about them when we talked about stars is brown dwarfs aren't exactly stars, in that they do not have nuclear fusion happening in their cores. They do not give off visible light because they are not hot enough. You can think of a brown dwarf as being an object that's sort of in between Jupiter, a big Jovian planet, that's just a big ball of hydrogen, and an M-type star, a big ball of hydrogen that is slowly fusing hydrogen into helium and giving off red light. In between there are big balls of hydrogen gas that are not quite heavy enough to fuse hydrogen into helium, so they don't give off visible light. But they don't orbit a star. They are their own big ball of hydrogen floating around the galaxy. And they can even possibly have planets orbiting around them. These objects are called brown dwarfs. Brown dwarfs are hard to see with regular telescopes. They don't give off light. Now that we've got a brand new infrared telescope, the James Webb, out there taking pictures of the galaxy, we might discover many more brown dwarfs in the next decade than we know about right now. We might discover that there are more brown dwarfs out there than we think there are. If we can imagine a planet or an icy, what we would think of as like an icy moon, a Pluto-like or Triton-like object, orbiting a brown dwarf, close enough to it that tidal heating heats its interior. Even though this object doesn't give off visible light, it just gives off some mild infrared radiation just due to gravity squeezing the hydrogen gas. We can imagine tidal heating being enough to warm this object under the surface, and it could have liquid water underneath the surface, the way we think Europa or Ganymede or Titan might in our own solar system. So we can imagine planetary systems that are very, very different from ours. In fact, around things that we wouldn't even exactly consider a star, that are habitable in unique, different ways from our solar system. That being said, because the easiest thing to imagine is what we know already, which is there can be planets around stars that give off plenty of light, that have liquid oceans on their surface and atmospheres and life that lives on the surface. That is the easiest kind of life to look for and to think about. So we will always default to thinking about Earth-like planets and Earth-like life until we do find life on an object like Europa or Titan or under the surface of Mars or what have you, that forces us to broaden our conception of what kinds of planets might or might not be habitable.